And you could verify that that's your guess, and if you verify that, you could say disprove that something's the encryption of a 0, that something's the encryption of a message. And so problems like this are always both in NP and co-NP. All the instances that you generate, even though it's an NP hard problem, and hence probably not in co-NP, all the instances that you generate are in co-NP.
Russell, you want to take a break?
1 minute. Okay, and so really, even breaking this encryption in the worst case wouldn't solve an NP complete problem. It would only solve a problem in NP intersect co-NP.
Can you break it with quantum computer?
I don't think it's known how to do that. I wouldn't be surprised if someone eventually did, but I think it's been tried. Okay.
But in practice, does this actually work?
It depends on in practice what in practice means. So first, it's not to get, there aren't good algorithms for breaking it, but in order to make it big enough that you can't break it by exhaustive search, you have to make it big enough that it's not really competitive with RSA.
The problem is the matrix is n squared, so it's a big key.
Yeah.
So people are not, some people have implemented this, but it's not widely used because of that. But if there was a factoring algorithm, they would.
Yeah, exactly.
Right,
It's like wind power.
Next best, if factoring was P, would that be the next best in practice?
Oh, well, I guess the discrete log. But I'm assuming the factoring and discrete log tend to go together.
Yeah, right.
So let's say they went down the tubes together. Then I think Michaelis would stand a fighting chance of being adopted.
Or different things that are sort of in the same spirit. Like the lattice things are somewhat in the same spirit. They have.
Yeah.
They're all also like a linear transformation with noise.
Okay, so I guess I'll continue after a short break.
This is this break that you talk about.
I was changing the tape, so I didn't
Okay, so let me. So the Michaelis system was in NP intersect co-NP because those instances that were derivable, you could just guess the mapping from the GAPA code to those instances and use that to disprove that something was the encryption of something just as easily as you could use it to derive the decryption. Okay, so and as Gilles Broussard observed way back in the early 80s, in fact, any public key encryption with perfect correctness, where there's no chance of decrypting to a false value, and there's no chance of sort of having a false start with your secret key or something like that, is the decryption function is in NP intersect co-NP, because if you guess the secret key, then you can use that to prove that it's not that something's not the decryption of something. So we can't expect any crypto system with this perfect correctness to be NP hard. So while that general system technique might occasionally produce good crypto systems, it won't do what it advertised and base the security on an NP complete problem. So the most promising approach, though, towards basing where we almost match between the problem that a crypto system is based on and an NP complete problem is in lattice-based cryptography. So it's NP hard to, I'm not going to define what a lattice is because there's nothing that's going to require that knowledge. So there's something called a lattice. It's a set of vectors. Finding the shortest vector or even approximating the shortest vector in the lattice is NP hard to within a certain factor. That's like n to the epsilon. Okay, it might be epsilon, might be a function like 1 in log or something. I forget exactly what it was. Okay, but on the other hand, there are these worst case to average case reductions that ITI came up with that map an arbitrary instance of the shortest vector problem into a random instance of the shortest vector problem. But the factor that you need to preserve, the approximation factor that you can tolerate is some more like n squared than this little n to the little o of 1. It's some polynomial. It's not too huge. It was pretty huge in the original paper, but it's gotten better over time. And but it's just slightly worse than what we can prove NP hard.
It's
Okay.
not clear what slightly means. Right?
Well, okay.
This is there's an easy range and a hard range.
Yeah. So
I guess that's the next slide.
no. Well, I mean, just the worst case hardness, and ITI and Dwork even modified that into a crypto system, and there are different variants of the ITI Dwork public key encryption system since then, based on the worst case hardness of some lattice problems. Not exactly the shortest vector problem, some more technicalities.
Regev did it exactly with the
okay, good.
With a quantum reduction.
Okay, yes. Some technicalities that I don't want to get into. Yeah.
Doesn't it contradict to that the decoding functions in NP intersect NP?
No, because so one thing is this slide it got sort of erased, is that many of the public key encryption functions based on lattices do not have this perfect correctness. They only have probabilistic correctness, and therefore it's not a certificate. Even if you map your randomized version to the original lattice, undo it, is not really a certificate that something's far from your lattice. So it's like what you can do is to use that to distinguish random points which are usually far from your lattice and points that are purposely chosen to be close to your lattice. But it doesn't actually certify. It's just that when you have a point that's close to your lattice, you usually find a point that's close. And random points you usually don't find, but it doesn't actually give you a certificate that there is no such point.
Russell, there is another reason why it's not a contradiction, is that all of these lattice systems are actually in NP intersect NP. Or that's the next thing?
Yeah. But although, yeah, exactly. Although the Broussard argument doesn't apply, all the problems, when you go to those approximation factors that I could actually prove something for, all those problems are actually in NP intersect co-NP. And if you look at the technique that he used to do the worst case to average case reduction, it doesn't quite put it in NP intersect co-NP immediately, but even if you didn't know that it was NP intersect co-NP, the reduction itself gives you a technique to show that to give a probabilistic argument that something's not close to a lattice point. So all the techniques actually, if you actually go at a lower level and look at the ITI techniques and not just use the result as a black box, they actually show that the problem's in NP intersect co-AM. And so still there doesn't seem to be any way of using this kind of result to go to the NP complete problem, even though it seems in a quantitative sense to be tantalizingly close. But as Avi points out, sometimes seeming quantitative changes can make qualitative differences. It could just well be that that you can approximate shortest vector to n cubed, and you can't do it to n squared, and that's the truth. So it's just enough to break the system, but not enough to contradict the NP hardness. Okay, so basically, so this means that we sort of have no real credible argument to base public key cryptography on something like P not equal NP. Well, that would be a pretty remarkable result, but, you know, so that's a strong thing. But so can we disprove that implication?
So before you go on, but if I weaken the assumption to, let's say, that I want to prove that NP different from ONP,
Yeah.
then this could still.
That could still, well, yeah, but we also don't have a really good way to base it on an arbitrary NP intersect ONP problem either, but
Yeah, but still.
yeah, that would be a great result too. Yeah. Okay. Now, okay, logically, disproving this implication, however, you know, says, okay, well, we have to do the following steps. Okay, and it's just a logically equivalent. We first prove that P really is different from NP. Then we have to say, okay, now we have to disprove that the public key cryptography is possible. So let's design a factoring algorithm and a discrete log algorithm and break the Michaelis system. And when we're done with that, we'd have to consider all the alternative crypto systems and break them all.
Sorry, I didn't get your point.
So logically, to disprove an implication, you have to prove the hypothesis and disprove the conclusion. That seems, in this particular case, that seems a very daunting task.
So we have the center of return.
Yeah. So maybe over the next 5 years we can do it.
We had 11 million then.
Yeah. But maybe we can give some kind of weaker evidence for this non-implication. So we could give more Broussard-style implications. Okay, so Broussard said, you know, with perfect completeness, then it's an NP intersect ONP problem. All the techniques we know give you some variance of that, like NP intersect AM or TFNP or something like that. What seems to be a proper subclass of NP. Okay, all the crypto systems we know of really are in a proper subclass of NP. So could we prove that breaking an arbitrary public key crypto system is in some proper subclass of NP? And now, of course,
What do you mean by it? So now there are too many negations. So you want.
we want to prove that even if P is different from NP, it's hard to justify a public key crypto system. That we can't just do it based on that assumption. We'll need some stronger assumptions. Okay? So one way of doing that would be, okay, we'll take some other implications that we don't believe, or even if we believe both the hypothesis and conclusion, we don't believe that implication is going to be provable. Like P equals NP implies P equals NP intersect ONP. P not equal NP, implies P not equal NP intersect ONP. The other version I can prove. So take some other ones, say that if we could prove the first implication about public key cryptography, then we'd get this other kind of implication that we also don't believe. Okay? By showing that public key cryptography always can be broken within a proper subclass of NP. Okay? So that would be a great result. I'd love to see a result like that. I don't know of any results like that. So I'll put it on my list of open problems and say, what other kinds of evidence could we give that this implication is going to be hard? So the other kind of evidence we could give that the implication is going to be non-trivial or hard is to take the standard style in which such implications are proved and show that no proof along those lines can prove the implication. Okay? Or we could combine the two and say any proof along the standard lines implies some non-trivial complexity thing that we don't actually believe.
So aren't there sort of deeper issues here, or you're kind of folding this under the table specifically?
I'm sure.
Public key cryptography, there is this implied or explicit randomness component. And also there's this kind of, it's not just got to be hard for one instance, it's got to be hard for many.
Oh, okay.
Difficult instances. I mean, how do you relate key versus key?
Can you hang on for a few minutes? Okay. This is good. We have to go from, one part is to go from worst case complexity to average case complexity, and that's going to be a big, we'll talk about that in hopefully just a few minutes. Okay. So what is a standard proof? Okay. A standard proof is almost always by reduction. And what we do is, when we want to say hardness assumption 1 implies hardness assumption 2, we say we have to have one part that gives a construction. You have a hard problem of type 1. How do I construct a hard problem of type 2? And another part that gives the reduction. If I've got a successful adversary for a problem of type 2, and that could mean average case or worst case or some even more stringent condition, then that will give me a successful adversary for problem 1.
Adversary is really a solver here.
A solver, right. Okay. So now, so that's kind of generic, and if we just talked about existence of pi 1, pi 2, adversary 2, and adversary 1, that wouldn't reduce the notion of proof at all. But we usually give at least some of the proof in terms of these black box constructions. So from adversary 2, we want to construct adversary 1. And what we usually do is we don't actually look at adversary 2. We just use its functionality. It's a breaker of problem 2, pi 2. And we use it as a black box inside adversary 1. Okay? So adversary 1, that should be, is a polynomial, should be polynomial time using an oracle. Well, you want to tell it what problem it's supposed to be solving. So we'll give it an oracle for pi 1, problem 1, and any adversary 2 that we could plug in, as long as it's a successful adversary for pi 2 in the sense of solving pi 2 on the standards that we're talking about, worst case, average case, or whatever. Okay, and almost all proofs of hardness, the implication between the hardness of pi 1 and the hardness of pi 2 are black box in this sense.
Particularly all the NP completeness results that
Yeah.
you learn.
Yeah. Okay. On the other hand, this is often also the case that the construction part is black box. That pi 2 is defined as a reduction with respect to pi 1. There are more counterexamples for this part than for the black box proof of correctness. For example, the NP completeness problems aren't black box in this sense. When you reduce an arbitrary n problem in NP to SAT, you're actually picking apart the algorithm for that problem, not just using it as a black box. Okay? So this is still true that the construction is black box most of the time when you have a generic result. Okay? So what we could do, so one thing we could try to do is
Wait, now, which one was type 1, which one was type? Oh.
type 1, you start with a problem that's hard for type 1, in the sense type 1, and you end up with a problem that's hard in the sense of type 2. Okay. So what you could try to do is say, okay, let's rule out black box proofs of security, black box reductions between the security of problems, and there are a couple of, at least a few known results, some by people in this room, of limitations on such reductions. Okay? So they say that for any problem of type 1 and any problem of type 2, if you've got a reduction between cracking pi 1 to cracking pi 2, okay, then pi 1 is not just crackable with that oracle. It's actually easy in another sense, like being an NP intersect co-NP or something like that. Okay, and in particular, if you can show that and you believe that NP is different from co-NP or some variant and polynomial hierarchy doesn't collapse, then you believe that we're not going to be able to do that starting with an arbitrary NP complete problem.
And R is a randomized reduction or?
Whatever reduction, usually randomized, whatever class of reductions we're talking about. So that has to be specified in the result. I'm just giving a general template for the kind of result we could prove.
But the results that are proven are with respect to randomized reductions?
Are respect to randomized reductions, but sometimes with certain restrictions. Like, so this is Bogdanov. This is a very particular kind of reduction, random self-reduction. This is Bogdanov and Trevisan has the non-adaptive. It's randomized but non-adaptive, and the other paper has a few more.
The reduction has to be between the worst case and the average case of say satisfiability.
Really, yeah. So that's for the first one. Bogdanov Trevisan could be worst case of satisfiability and average case of any problem, and AGGM is worst case of satisfiability and inverting almost any one-way function. And there's certain restrictions on what kind of one-way function.
Who's AGGM?
Adi and Dana. Yeah.
Sorry, it would help me, just because I'm getting lost in
Yeah.
the generality of what you've written there. So you just gave a couple of examples. But maybe-
Right, but I'm going to go through those examples in more detail, saying this is the type of thing we could try to prove. Okay, and that would this gives us a restriction on any proof of correctness that's black box. The construction needn't be black box, is the point. But it's usually under some assumption. Okay. On the other hand, if you've got a fully black box proof, where both the construction and the proof of security relativize, then since everything's black box, it doesn't really matter if we add some more black boxes to the situation. If we add an oracle that all parties can access, then the pi1 relative to this oracle is still pi1 prime, and so pi2 prime makes sense. It's just computable using the oracle, and the adversaries make sense, and so on. So any kind of fully black box proof relativizes, okay, in the sense that if it's true, if we've got such a proof, it's going to hold not just for actual complexity, but complexity relative to any oracle. So, to prove a limitation on fully black box reductions, where both the construction and the proofs of security are black box, what we can do is give an oracle O where there is a hard problem of type 1 and there is no hard problem of type 2, and give a model where the implication really fails. And even though it's a weaker kind of reduction that we're ruling out, or stronger kind of reduction that we're ruling out, and so it's a weaker result to rule it out, it has a bonus of giving you a model that tells you sort of what would a world look like where the implication failed. Okay. I did write that on a slide. Okay. So now, to go all the way from NP completeness to public key cryptography would be a big step, would be dramatic change. We could break this down into a series of steps that we would have to do. Okay? I think the main steps are, as you were saying, we'd have to go from worst case complexity to average case complexity. Okay? Then, say the average case complexity actually isn't enough. We need average case complexity with some leverage. That's a one-way function. We'll see that in a second. Okay. And then it turns out that it's actually a hard problem to go from a one-way function to public key cryptography. So those are the three barriers: worst case to average case to one-way function to trapdoor. Those are the seeming barriers. How many of them are actual barriers to what kinds of proofs? Okay, so I'm saying, we do really have to go to average case complexity, because worst case complexity, when it comes to security, isn't saying much of anything. So I don't know, can you, usually attackers don't really need to have to have 100% surety of the attack succeeding before they'll do it. They're willing to take a few risks, especially if they're exponentially small chance of being caught. Okay, so that courier probably didn't live long, but he had a twin that we'll see in a second. Okay, so we have to go from worst case hardness, worst case hardness just guarantees that for every adversary there exists some inputs on which it fails, to average case hardness, where it's reliable that the adversary is going to fail. Okay. And
remind people that you are going to prove that these are unlikely.
Each is
unlikely.
That's what we're hoping. Yeah, so what I'm trying to say is, okay, or just pose the question of, can we use standard techniques to prove these implications? I think the implications themselves are likely in the sense that both the hypothesis and conclusion are true. Okay? But they're unlikely in that standard techniques are going to make it difficult to, they're not going to be provable by standard techniques. We're going to have to do something else to prove them.
Does it mean that these implications are unlikely, that the original implication is also unlikely? Because you don't have to necessarily go through these steps.
No, you do have to. All the implications in the other directions are all logical. Okay, public key cryptography implies one-way functions, implies hardness on average, implies worst case hardness. So if you manage to short circuit and go all the way directly to public key cryptography, you could complete the cycle easily. And they'd all be equivalent. So logically, you do have to go through the steps. Not clear that practically you would have to. Okay. So, Bogdanov and Trevisan, on the other hand, showed that at least for a large class of reductions, if you've got a reduction from the worst case complexity of L to the average case complexity of L prime, then L is in this class that's just slightly above co-NP. Similar in spirit, but slightly above co-NP. And so, so it would follow that if the worst case, if we could have this implication via these non-adaptive reductions, then for an NP-complete problem, then the polynomial hierarchy would collapse. I think it's not quite to that level, but. So if you have any language whose worst case complexity reduces to the average case complexity of a language in NP, then that language, under non-adaptive reductions, then that language is in co-Arthur Merlin/Poly. And you note that, remember, so one example of a problem that does have that kind of reduction is the shortest lattice problem. Itai's work showed that approximating the shortest lattice reduced to random instances of approximating shortest lattice, which is a problem in NP. So this would, since Itai's reduction was was non-adaptive, that that does mean that you would get, that the collapse that we, the lower complexity that we saw as a result of I-type specific reduction does follow from these kind of general, for this general reason.
Maybe it's worthwhile to explain what an adaptive maybe.
No,
No?
because I want to get, we want to get to lunch, and I want to talk. Yeah, we have 20, if we have 20 minutes, I'll get to the end of my talk if I don't make digressions at this point.
Okay.
Okay, so we could also ask if there are oracles separating the two, and I was writing down slides this morning to present the outline of such an oracle when I realized it was full of nonsense. It was complete nonsense, and I don't know of such an oracle.
I think that there are things known like that.
I think I claimed a long time ago that I had such an oracle, and when I was giving the details this morning, it fell through. I don't know of anybody else who would made similar claims.
Everybody assumed that's.
I never published, but I never published it, so that shows that you should not believe something until it's published. But
Ask Scott.
I'll ask Scott and Lance, but I'm pretty sure I haven't seen it. And okay, I think if it's not known, then it's a pretty interesting question.
And you can certainly make P and NP equal, except make them unequal just on really wide-spaced instances, which is kind of,
That's not the same, because because even on those lengths, when they're not equal, they could be hard on average.
What did you make?
Okay, so I'm just going to go on. I'm sorry. Okay. Well, okay. So at least the Bogdanov-Trevisan gives us a reason why we can't expect to prove that hard on average problems are NP complete. But lots of problems seem hard on average. We even have Levin has a notion of complete on average problem. So why don't we just drop our goal, instead of basing things on NP complete problems? Let's base cryptography on average case complete problems. Okay, but that's still not quite enough.
That hard on average with respect to Levin's notion?
Yeah. Yeah. So let's have a new, because we could have these very hard problems that no one can solve, and I claim a problem that's so hard that absolutely no one can solve it is pretty much as useless as as a problem that's only hard in the worst case. So I don't know if you can read this. I sort of wrote it. So this is the new courtier with a new security plan. He's built the throne room so secure that absolutely no one can get in. Not even a mouse. And his job security is not too well assured either. Okay, so you have to make some asymmetry between the legitimate users and the attackers. What's the asymmetry? Well, the only real asymmetry there is maybe the legitimate users are the ones posing the problems. Okay, so to distinguish the legitimate users from the attackers, we need to construct random hard problems, but in a way that we know the solutions. The person constructing the problem knows the solution. And so you could say, well, it's some kind of probabilistic process where on a random tape you generate a problem and a solution, and then you have some definition of what makes a solution really a solution. And you want, with high probability, the output, the supposed solution really is a solution according to that definition, but it's hard to find any other solution. So that's kind of complicated, but fortunately there's a canonical form of such a problem, the one-way function, where you have a function that's easy to compute but hard given a random element of the range, or a random element of the domain, a random element according to the map, starting with a random element of the domain. Finding another element in the pre-image is hard. And you can see that actually just a little tweak shows that the two notions are just purely equivalent, and this is the standard canonical form of such a problem. Okay. I'm going a little bit fast because that should be review, and we don't have, I want to get to lunch. Okay. Now, there's a great theory of one-way functions and their applications in cryptography. This is probably one of the best success stories around, in that we know exactly the existence of one-way functions is necessary for any kind of cryptography, for the sort of reasons I sketched before, and it's equivalent to the existence of many fundamental concepts in cryptography, like pseudorandom generators, very secure private key encryption, bit commitment, non-trivial zero knowledge, and strong signatures. Okay? So it's kind of counterintuitive in two ways. So Diffie and Hellman said, I'm going to introduce this notion of public key cryptography in addition to, in contrast to private key cryptography. Public key cryptography is going to have a foundations in complexity theory. Okay? Well, 30 years later, public key cryptography has no real foundations in complexity theory, but private key cryptography, wow, that's great. That's got a great theory. Okay? You know, we know exactly when private key cryptography exists and how to make them, sort of. Okay? So, and the other thing is that public key cryptography had two aspects, encryption and signatures. Signatures were supposed to be something you couldn't do with private key cryptography. It turns out that signatures is equivalent to strong private key cryptography, which seemed to be totally distinct from Strong's public key cryptography.
Well, except that all the practical private key schemes have no basis in theory.
Okay, yes,
Usually
but
the primitive itself has no basis in theory, but then the combinations you do on it, you don't use it directly, and that has lots of basis.
Yeah, but you can also, by translating things in terms of one-way, you know, so you can say that you at least know what you're assuming about this private key system, or at least sometimes. And then they assume all sorts of things that are hard to classify, like pseudo-randomness, even if you know the key. But you know, what we need in order to do private key cryptography, even if they don't do it that way. So, okay. So how about getting a one-way function? You know, how hard is it to get a one-way function based on principles? Okay. Well, so there's still some bad news. Adi, I should say, Oded, Shafi, and Dana show that if we've got any language that reduces to inverting a one-way function, so if we then it's also in this probabilistic version. That language is also in, should say, it's in, that should be co-AM rather than AM. It's also in this probabilistic version of co-NP. Okay, so we won't be able to do that with an NP hard problem. Although that wasn't, we were sort of beyond NP hardness, so I want to just ask, I think this is probably implicit in the paper, is whether there's some kind of average case version where you could say that if you've got a problem L whose average case complexity reduces to inverting a one-way function, then L has an average case algorithm in co-AM. So a co-AM procedure protocol that does the right thing almost all the time.
So this is also non-adaptive reduction?
There are two results. One is for non-adaptive reductions, but the other is for adaptive reductions, but make some assumptions on F.
Why is this bad?
Why is it bad?
It's another implication.
He means co-AM there.
Yeah, but still. It's another implication that's
Yes,
unlikely, or we
Yeah.
cannot prove it using
Yeah.
It's bad because it's going.
COIAM, yeah.
Co-AM, sorry. Okay. So it just means that there's a limit to what kinds of average case problems, what kinds we could base one-way functions
so it's
on.
an NP to start with?
It's almost always an NP to start with. So it's, I should say, right. I think probably what you get is as an AM intersect co-AM, but usually the application is to problems already in NP. I mean, you could start with a problem, okay.
But I still don't see why it's bad, because for instance, factoring, it's in...
Yeah, but that's a problem where we can, but you're saying, can we go beyond that? So, are we stuck, is all public key cryptography based on NP intersect co-NP? It might be. Okay. So we could also look at oracles that tell us something about one-way functions. So one thing that oracles will tell us about a one-way function is that if we take an oracle for a random function, it's an ideal one-way function. It's not just one way, it's sort of one way in the strongest possible terms. Okay? And here we're looking at f as an oracle, so adversaries also have oracles for this random function. Okay. Now, indirectly, this tells us how to actually construct an oracle where there are no one-way functions, but there are hard on average problems. So let's first get rid of any kind of complexity there is except for the oracle. So start with an oracle that makes P equal NP, like P space. Now let's pick this random f, but instead of giving the people an oracle for f, we'll give people an oracle for the graph of f. So in other words, given a pair x, y, the oracle will tell you yes or no, is y equal to f of x. Okay? So g sub f is strictly weaker than f, so inverting f given an oracle for g sub f is even harder than inverting f given an oracle for f. So that's still a hard problem on average in NP. Okay? But on the other hand, you look at this queries of this oracle, they're so sparse. They're only exponentially small probability that any one query is in the oracle, that when you simulate a person generating problems, making probabilistic decisions and making queries to this oracle, you can simulate the oracle answers as no. The oracle doesn't give you any good help in generating problems. And so there are hard problems out there, but we can't have any kind of asymmetry between the person generating it and the person trying to solve it. So there are no one-way functions. So that says that we can't have a fully black box reduction between an average case problem, a hard problem, and a one-way function. And it also tells us that these random functions are great for private key crypto, and that when we're designing a private key crypto system, then we should be shooting for a function that's as random and unstructured as possible, because those are really the best one-way functions. That's a little bit heuristic, but at least it gives us that impression. In contrast, work of myself and Stephen Rudish show that if P equals NP, then even if you give me a random oracle f, okay, secret agreement and hence public key cryptography are not possible to do securely. Okay, and Boaz and Mohammed have an improvement and simplification of this result that they're publishing soon.
It's on the archive.
Yeah. Okay. So that says that with fully, on one hand, it says that fully black box techniques do not show that one-way functions imply public key cryptography, because this random function is an ideal private key or one-way function, but it's not helpful to do secret agreement and hence public key cryptography. And it also gives you the impression that these random functions aren't the way to do public key cryptography. And maybe that's why we keep on relying on these more structured mathematical problems. It would be kind of interesting to see how unstructured and combinatorial we could get a private key cryptography system to look like. How much like a random function we could get it to look like.
So, I mean, the point being that, I mean, you have that hypothesis that P equals NP. Blah, blah,
Right.
blah.
So the P equals NP is to get rid of everything that we saying like ignore your, if we didn't have that we could say, oh well, ignore the oracle, just use RSA to do your secret agreement. Okay. So the oracle is to get rid of the P equals NP part is to get rid of anything that doesn't rely on the oracle. To just look at the contribution of the oracle and zero out everything else.
It's more or less to force it to be black box using
Yeah.
random function.
So, okay. Even sort of more distressing, okay, Stephen Rudish has a family of oracles where for every k, there is an oracle O sub k relative to which you can do secret agreement in k plus 1 rounds, but not in k rounds. Okay? So unlike so that says that you can't sort of take even a secret agreement, which is very close to public key cryptography, and from that get down the number of rounds to 2 and hence hope for public key cryptography. Okay? And it also suggests that we can't even have some kind of normal form for secret agreement protocols where you take one secret agreement protocol and you map it into a fixed kind of exchange pattern. So maybe there should be one, that this gives us a whole infinite hierarchy of complexity assumptions about secret agreement.
That would be a secret agreement complete problem.
Yeah, I wonder if there could be one, because that would seem to be at some level of this hierarchy.
And indeed, is it legitimate to talk about secret agreement complete problem, or do they talk about complete problems in cryptography?
It makes sense, but I don't think people have many results about them. There, for example, Levin does have a complete one-way function that I was sort of omitting, a function that's one-way if there exists a one-way function that he gets by merging all possible one-way functions together. That's the closest example I can come up with. So what we can conclude from this is that public key cryptography is much more fragile than cryptography in general. We don't have to, we're assuming something that's different from just having a sufficiently hard random thing out there. We're having to have some kind of structure, and that seems essential to public key cryptography. And it doesn't seem to be equivalent under at least the standard kinds of reductions to any of the other better understood assumptions that we talked about. Okay, so let me quickly go through, in the 0 minutes that are left, go through some open problems I think people should be working on. Okay. So first, we want to improve the plausibility of public key cryptography. We want public key cryptography to be possible. We want to find some kind of justification for it. Okay. So we'd like to find public key cryptography with less structure or less obvious structure. Okay. And I think that's going to feed into the talk after lunch. We want to characterize. Maybe we could still give a characterization in, like we did with one-way functions. One-way function is just a problem where you can generate hard instances with solutions. Maybe we could give a similar characterization for public key cryptography. Okay. It would sort of clarify what the relationship is. Wouldn't give the, spell out all the implications totally. And let's try to find consequence. So why should we believe that P is different from NP? Because P equals NP, a world where P equals NP would be too good. Right? We could solve all these problems for free without having to think about them. How about on average? Well, still that would be too good. Even if every problem in NP were easy on average, again, you wouldn't really have to think about problems much. You would just solve them automatically. Okay. A world without one-way functions, there's a result of myself and Leonid Levin that says in some sense you could do things like universal data compression, and average case learning. Okay? So you get some positive consequences from that. A world without trapdoor functions? Are there any benefits? More benefits, we could say, the more algorithms that we would get for free from them not existing, the more credible it is that they exist, in my mind at least.
But from a generic assumption that they exist.
Then a generic assumption, trapdoor functions don't exist. Yeah. Okay. So then the other thing that we could work on is try to give more evidence that we can't base public key cryptography on an NP-complete problem. And as I said, the one way we could do that is to prove that breaking a public key crypto system is always in some proper subclass of NP. Or that some weaker assumption than P equals NP, seemingly, implies that public key cryptography is impossible. Okay. Finally, a general challenge, and if you read our grant proposal, it's in big letters there, is to go beyond these black box methods that we saw were so limited and somehow use the code of a one-way function to insert a trapdoor or use the code of the adversary in the reduction, not just use them as black boxes. And then finally, we want some more results to say our assumptions are truly distinct. The 4 levels of assumption is what I'm talking about in particular, saying there's some results about, as I mentioned before, about absence of certain classes of reductions between these concepts. They have some technical restrictions. Let's get rid of those. You know, that's a reasonable open problem. And prove, you know, so far what we have is such a gap between worst case and average case hardness and between worst case and one-way functions. Well, there are at least 3 other gaps that we could be talking about. And if we look at secret agreement and different forms of secret agreement, that gives us even more. Can we come up with similar non-reducibility results for some of these other levels? Okay. And finally, as I was doing the talk, I realized that I didn't know any oracle relative to which P was different from NP, but hard and average problems, but no hard and average problems in NP. Can we give such an oracle or give a relativizing proof that hardness on the worst case really does imply hardness on average? Okay. So I think that was it.
Questions?
Hi, Martin.
So I have one question about structured problems. So
Yeah.
is there any good definition of what structure means? For instance, like there is a homomorphism or automorphism, like a large automorphism group.
Yeah.
Or so did anyone try to create a definition for that?
So I'm using this, you know, I used the phrase just heuristically in this talk. I don't think it's something that's, you know, I was trying to raise an issue that I don't think is actually explicitly addressed in the literature. So I'd have to say there isn't any kind of standard notion of structure. It's more like you know it when you see it. Having a more formal definition would certainly be useful.
One form of structure is being in NP intersect co-NP or AM intersect co-AM as
Yeah.
opposed to being NP complete. So that's
Sort of
one.
a good characterization.
Yeah.
Any other questions? Okay, so the lunch is down there, and actually it would be great if when we go out, we could stand in a group and
Take a picture.
picture for our website.
Great.
Group.